ready to go. Cool. All right. Good afternoon, everybody.
Howdy.
Dang. No way. Thank you for saying howdy. I appreciate that. What about the rest of you guys? Is it not a good afternoon? Is it a bad afternoon? It's Friday. It's Friday afternoon. That's got to count for something, right?
It's a test Friday.
What's that?
It's an exam Friday.
For you?
More.
Not for you guys.
For different classes.
Oh, for different classes, yeah.
Yeah, we're starting to get into like if you have
Yeah,
not
it's
like
like-
actual midterm season, but like if you have multiple tests, usually this is around where like a lot of them will be.
Yeah.
So I think especially a lot of engineering majors are going to be hating themselves right now.
Yeah, they all
But,
seem to come at the same time. Yeah. All right. Are there any questions, comments, concerns before we get started? Don't forget that the Unit 5 assignment's due next Wednesday. And also due on Wednesday is going to be your first exam. Don't forget the first exam is going to be available on Monday at 8 o'clock in the morning. And it will be due that Wednesday at 11:59 p.m. at midnight.
So one of the people in the Discord, so they just said, is he talking? So I don't know if they can hear you, Mike, but one of the people in the Discord had asked, will the assignment 5 questions be on the exam?
Yes, the assignment 5 questions will be on the exam. Can you guys hear me? The little lights lighting up. Liam can hear me. Okay. Yeah, so like I said, don't forget to manage your time appropriately. Both the Unit 5 assignment and the first exam are both going to be due Wednesday at midnight. So my advice is go ahead and knock out the Unit 5 assignment now, so you don't have to do it on the exam. It's not too bad. It's a lot shorter than the other ones have been. In fact, the assignments overall are going to be a fair amount shorter moving forward. So, all right, anything else? Well, cool. Well, we are in Unit number 7 now. We skipped over Unit number 6 because it's kind of an extra topic that doesn't really relate to anything. Just an alternate way of optimizing Boolean expressions, but we spend a lot of time optimizing Boolean expressions, so we're going to move on to some new stuff. Starting with today's topic, multi-level gate circuits. So in a similar way to how we came up with a structure, a way to optimize our Boolean expressions, here we're ready to actually start making stuff, right? Designing circuits to do different things, and kind of in that same fashion, we're going to come up with a system for designing or laying out our circuit designs. I can wake my phone back up. All right. So, first thing we need to do is give ourselves a definition to work with. And that definition is level of gates. So we say multi-level gate circuits. Well, what does it mean to have a level of gates? And the definition here is the maximum number of gates connected in series between the circuit's input and the circuit's output. So the level is just the maximum number of gates connected in series between the circuit's input and the circuit's output. We'll do an example to show what I mean by that here in a second. There are 2 sort of bullet points that we need to make. The first is that we assume that all variables and their inverses are available. Basically, we don't count the inverting of our inputs, right? So we just get A and A prime for free. The use of the NOT gate to give us A prime doesn't count for this analysis. It's its own thing. And also that levels consist of the same types of gates. Now this isn't a hard and fast rule, and we will break it from time to time, the same types of gates. But for now, to keep things neat and organized, we're going to say that every level has to have the same type of gates. A level can be AND gates, a level can be OR gates, but a level can't be AND gates and OR gates.
Did that say levels?
Yeah, but I forgot the L. Levels consist of the same type of gates. All right, so let's do an example. So we'll just draw a logic circuit. Input A and B into an AND gate. Also down here, you're going to have inputs F and G. Also into an AND gate. Then we'll have an OR gate that takes the input from the A and B gate and also has its own inputs D and E. Another OR gate that has input C, and they feed into an AND gate, which then turns into an OR gate with input H, and there's our result. We'll call it Z. So that's a logic circuit, and it's got some levels. We always start when we count the levels from the end and we work our way backwards. There's some important reasons, some important algorithms that we're going to implement that rely on this fact. So we'll start with we'll say the level that contains this first OR gate is level 1. Then we have this AND gate, that's level 2. We have another collection of OR gates, that's level 3, and then we have these AND gates, that's level 4. So this is what we would call a 4-level realization of Z. Now often, instead of drawing the logic diagram and figuring out what's going on, we can use a shorthand notation that comes right off the Boolean algebra. That's called a tree diagram. Tree diagram. So let's start with our expression for Z. We'll use the same one as we had up here. Now let's see. We had what A and B or D or E. And that got ended with F and G or C. And that got ORed with H. So what we'll do is this. We'll take each of these operations, we'll kind of create a branching structure off of them. So we'll say A and B are coming together. And also we had F and G, and those combined in the OR gate, so those are all on the same level, and those guys are going to combine the OR operations, just like that. Same thing for the other one. And then finally, these two groups got ANDed together. That, and then the result of that AND operation got ORed with H. And so there we have our sort of tree structure. Any questions about how we built the tree? All we did was just take the operations and just sort of cascade them down as they happened. And then what we'll do is we'll come up with some metrics that we'll use to kind of quantify the expression. So the first one is the number of gates. And that's going to be everywhere where branches came together. And we'll sort of draw a dot, a node, at all of those places. So how many gates were used in this realization? 6, good. Let's count the dots. The next thing is going to be the number of gate inputs. And this is the most important metric. You're trying usually to minimize the number of gate inputs. And the way you do that is just by labeling each node by how many inputs it has. So 2, and 2, this one has 3, that one has 2, that one has 2, and that one has 2. So how many inputs are there?
3, 2,
You add them all up. There are 13. Very good. And the last thing we care about is the number of levels. And again, if you drew your tree diagram correctly, everything will be kind of stacked in different levels, or kind of all in the same row. And I can see I kind of messed this up a little bit in my diagram here. But that's level 1. That's level 2. That's level 3. And of course, that's level 4. So 1, 2, 3, and 4. So there are 4 levels to the circuit. So that's how we use a tree diagram to quantify our logic circuit using the Boolean expression. Pretty simple stuff. Any questions about that? Okay. So let's define a little bit of terminology that we're going to use to describe our sort of standard circuits. And we'll give a few examples here. Let's say that first we have this. This is if we say and dash or. Well, by that I would mean a 2-level circuit composed of a layer, a level, not a layer, that's a different thing, a level of AND gates followed by a single OR gate at the output. And that might look something like this. I might have a handful of AND gates, and they all have some different inputs, and they all feed into an OR gate. Right. Now this corresponds nicely to which of our standard forms of Boolean expressions? Exactly, yeah. So when we have a sum of products, expression, we get an and/or circuit. Does that make sense? All right, next up, well, if we flipped it over, we had an or and. Well, that would be also a two-level circuit. Composed of a level of OR gates followed by a single AND gate at the output. Of course, that would look something like this. We would have a single, whoa, that got weird. A single level of OR gates, again, each with possibly various numbers of inputs, and they would all feed into a single AND gate. And just like the AND OR, which gave us or came about from a sum of products, the OR AND is the other one, right? A product of sums. Now we could also get a little bit longer than just two levels. If I add gate words here, such as OR and OR, well, that's going to translate to a three-level circuit. Composed of a level of OR gates followed by a level of AND gates followed by a single OR gate at the output. The last one is always just a single gate. So OR AND might look something like this. We got OR gates, maybe 3 OR gates, maybe 3 AND gates. The OR gates all have inputs, and this is just a quick sketch. And an output, and then maybe this one is from those 2 AND gates. And at the end, they all feed into a single OR gate at the output. So, is everyone going to get the gist of the structure of the terminology? So that circuit that we started with in our example, I scrolled all the way back up here.
Can you say that one more time?
Stay where?
That would be short.
I was going to come back to you. Also, don't forget, these are, what I'm writing down here is available for you in the class notebook on OneNote. So, all right. Okay, so anyway, so I'm going to scroll back up to this circuit. So how would we describe this circuit?
And or.
exactly, right? Yeah, so we would say that this is an and, or, and or. So a 4-level circuit consisting of a level of ands, followed by a level of ors, followed by a level of ands, followed by a single OR gate. All that just to make sure that we know what we're talking about. And then finally, there's one last version of this, which on the list is 4, and this would be a circuit of and or. Anytime you see this statement, this just means a logic circuit composed of AND gates and OR gates in no particular order. So this is a circuit where it's all just soup, right? There's no organization to it whatsoever. Okay. So what I'd like to do for the rest of class here is work one example basically where we're going to start with a function and we're going to kind of explore what it's going to look like in different standard forms. So, example, I'm going to say this, explore different forms to realize the Boolean function f, which is a function of a, b, c, and d, and is equal to the sum of minterms 1, 5, 6, 10, 13, and 14. Now, no matter what form you're working in or what form you want to realize your logic circuit in, you will always start with this, and you'll always start by using a K-map to get the minimum sum of products or product of sums. So you'll go to that place and you'll start there, because getting that minimum solution does like 90% of the heavy lifting for you, right? It's going to get you most of the way to your optimal solution. So we'll start with that. And to do that, we'll go ahead and do it with a K-map. 2, 3, 4. All right. So it's a 4-variable map like we worked with on Wednesday. F, A and B on the top side, 0, 0, 0, 1, 1, 1, 1, 0. C and D on the bottom side, 0, 0, 0, 1, 1, 1, and 1, 0. And we're going to go ahead and label everything in. So let's see, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So to kick things off, let's go ahead and find our minimum sum of product solution. That's by grouping the ones, and there's not a whole lot that we can do here to make it interesting. Since they're in these little rows of 3, can we group them all? Can we group all 3 of them together? No, right? Because remember, it's got to be a power of 2, so that means the best that we can do is sort of this business. So let me write my solution down here. F, function of A, B, C, and D. That's going to be equal to, so this first grouping is going to give us what, A prime, C prime, and D. Or, let's see, this second grouping is going to get us what, B, C prime D. Or, let's see, that grouping, that's going to get us B, C, D prime. And this last group is going to be what, A, C, D prime. Cool. All right. Now, and also, while you're here, it's usually a good idea too to go ahead and also grab the product of sums form. F is still a function of A, B, C, and D. And now we're going to have some things like, let's see, this top row. Now remember, we're doing the zeros, so that top row is going to become what? It's in the C equals 0, D equals 0 row. So it's going to be, or everything's inverted. So C or D. And if we do this third row of 4, that's at A, that's at CD is 1, 1. So that one is going to be C prime or D prime. Let's see, the next thing we do is these groups of 2. So that first one will be, what do we got? It's going to be A prime or B or D prime. And then this bottom group of 2 is going to be what, A or B or C prime. So now we've got both of our forms, our minimum sum of products and our minimum product of sums, and we can sort of use them both interchangeably depending on what sort of realization do we want. So let's start by just taking a look at the two basic ones that come right off of these two minimum forms. So let's say first, let's take a look at realizing it as an AND OR circuit. And that's just going to be straight up the minimum sum of product solution that we had. So we got A prime, C prime, D, or B, C prime, D, or B, C, D prime, or A and C and D prime. And we're going to go ahead and draw that tree diagram, which is going to be pretty simple. If I can get one node to cooperate. The tablet gets sleepy at the end of the day. Alright, fine. Just draw the lines. Alright, so those all grouped together. That's going to be one level. Okay, and we'll tally up the number of gates. 1, 2, 3, 4, and 5. So we can say the number of gates is equal to 5. We'll list the numbers. That's 3, 6, 9, 12. And it's got 4, so that's going to be 16. Whoa, that's a new one. One node just crashes altogether. Okay. All right. Where were we? 3 and 4. So the number of gates here was 3, 6, 9, 12. Plus 4 is 16. And then finally we had a level 1 and a level 2.
Isn't it called gate inputs?
Yes, ma'am. Or gate inputs equals 16. And the number of gate levels equals 4. So there's our analysis there. All right. And we could draw it if we wanted to, but for the sake of time, I'm not going to, because the tree diagram still tells us pretty much everything that we need to know about it.
Did you read about 4?
What's wrong?
Man, I'm just all over the place today, man. 2 is what I meant. All right. So let's take a look at the next one. Let's do the OR and that's going to come from our product of sums, which was C or D and C prime or D prime or A prime or B or C and that's all over the place. A prime, AB, C prime or A prime, B, D prime. And we're going to get a tree diagram that looks pretty similar to the one we just did. Just like that. And again, we'll tally up the number of gates. 1, 2, 3, 4, 5. So just like before, we have 5 gates. The number of gate inputs. So we got 2, we got 2, we got 3, we got 3, we got 4. So the number of gate inputs equals what? 2, 4, 8, 5, 11, 12, 13, 14. And the levels, we got level 1, and we got level 2. So our gate levels is 2. Okay, so between those two realizations, Which one is the more optimal solution? Someone is not maintaining professional discretion on their cell phone. Or pretend to hide it.
Or and.
What's that?
It's or and. To your answer.
Wait, what'd you say?
Or and is the answer to which one's the better one.
I like that. That's a pretty slick move, man.
I was thinking so too.
Put your phone away. Oh, I know you're paying attention. Like I said, I don't mind if you're on your phone. I just mind that you're like this on your phone.
Right.
Like I said, you can stick to the side. I mean, I can only see like half of you anyway. So like, as long as you have it, just have your phone on the desk, I won't be able to see it.
Right.
All right. Yeah. So the or and is the more optimal solution, right? And why is that? Because it's got less gates. Yeah. Or see, not that it has less gates; it has the same number of gates, but it has fewer gate inputs. And at the end of the day, gate inputs is what turns into transistors, and transistors is what turns into dollars. So, and power consumption and speed and all kinds of other stuff. So what we're looking for is number of gate inputs. So next up, let's try another popular form. Let's do or and or. Let's see what that does for us. And to get this one, we're going to start from our minimum sum of products solution that we had before. So we got A prime, C prime, D, or B, C prime, D, or B, C, D prime, or A, C, D prime. Okay. Yes, ma'am?
Wait, so you said if the gate inputs matters, what if they have, like, let's say both of them have the same number of gate inputs, same number of gates, but one of them have more gate levels or somehow?
I don't think that's possible.
I mean, like, okay, like, they have the same number.
Maybe it was. Then you would, if all other things being equal, then you would still go with the smallest thing, right? So if it had the same number of gates and the same number of gate inputs, you would go with the one that had fewer levels. Yeah. So essentially, you look at gate inputs as your deciding factor, and if they're tied, and then you can look other places for your tiebreaker. So yeah. So like I said, so gate inputs is the only thing that really matters. Then if those are tied, then you look at the other things. So let's see, or and or. To get this one into the or and or, we start with the sum of product solution, and we're going to look for terms that we can factor out, such as these first two terms, the C prime D and the C D prime. And the third and fourth term will let us create a thing that looks like this. C prime D or A prime or, and A prime or B, or C D prime and A or B. And again, we'll throw down our tree diagram. Here, kind of, again, adhering to the order of operations, the first thing that's going to happen is these ORs. So those guys. Those guys. And then the next thing will be the AND operations that happened. And the last thing is that last OR operation. All right. So now let's take a look. Number of gates. Equals, let's see, 1, 2, 3, 4, 5. Gate inputs, our magic number. Let's see, 2, 2, 3, 3, and 2. So it's going to be what? 12, right? And our levels, we have level 1, level 2, level 3. Just like that. So our number of gate levels equals 3. So number of gate input. Yes, sir.
I was just wondering, can you see the edges of the graph as the gate inputs and the nodes as the gates?
Wait, say that one more time.
So like, from graph theory, like just assuming the edges are the gate inputs and the
Yeah.
nodes are just the gate inputs.
Absolutely, yeah.
Gates.
All right. So from this one, what's our optimal solution? This one better than the other ones? This one has 12, oriented 14, and we're at 16. So despite the fact that this one has more levels, it has the fewest number of gate inputs, which means it's an optimal solution. It's going to be a more cost-effective solution to build. Does that make sense? Cool. All right, let's see. Only got a few minutes left, so I think we're going to leave it there. All right. So there we go. That's how so we've got some terminology to define these things. So we got and, or, how do we list them all out? And we can draw the tree diagrams to quantify kind of how optimal our solutions are, right? So we learned before in unit, or kind of in the lead up to this, we talked about how do we take our thing that we want to do, that's the truth table, that's the generalized midterm expansion, that's the thing we're trying to build. We use K-maps to get an optimal Boolean expression. That gets us like 90% of the way there. And then we're going to look into how can we tweak these forms just a little bit to get more optimal solutions. And then we'll see next week, we're going to take that a step farther by implementing NAND gates and NOR gates, which are the smallest, cheapest, fastest logic gates to build out of transistors. How we can take all of these and convert them over, all of these circuits, and convert them so that all the gates are just NAND gates, is what we're kind of shooting for. So Liam asks, would a lot of levels increase processing time as the circuit waits for inputs to cascade down? Yes, that's one of the reasons why we're going to convert everything to NAND gates or NOR gates to kind of speed those things up. And there are lots of reasons that we'll talk about throughout the rest of the semester why sometimes having more levels is still a good thing than having, you want depth, not like wide, deep level, like wide levels. So anyway, but that's something we'll talk about in a couple weeks. Any other questions, comments, concerns? Don't forget to get your Unit 5 assignment done so it doesn't get in the way of you getting your Exam 1 done, because that Exam 1 is worth a whole lot more than that Unit 5 assignment. So if there's nothing else, like I said, don't forget, Exam 1 is going to arrive Monday at 8 a.m., and it's going to be due Wednesday at midnight. So, and it's just Units 1 through 5. So this stuff that we just talked about isn't on that exam. Also, the Unit 7 assignment is available if you want to get started working on that. So if there's nothing else, have a good weekend, be safe, and I'll see you guys on Monday. Thank you.
Professor, how do we check to see like what we got wrong on the assignment?
You gotta talk to Max.
Well, I emailed him and